Okay, so last chapter of this section, and we're covering ANOVA. So we've been doing t-tests. So we had a single sample t, dependent t, and independent t, which is what the second slide is. So this is a summary of everything we've done. So one person is the z-score, one sample with the sigma is a z-test, one sample without sigma is a single sample t, one sample tested twice, paired samples, two samples, independent t. So that's like a summary of the last test and this one. And I have these at the front of each chapter just so that, like, when you're trying to find it, if you get a question, they're always kind of in a place you might be able to look and compare types of tests. And then all the different distribution names. So this is the same one we looked at last time, and really the biggest difficulty is the difference between paired t, where it's mean differences, and independent t, where it's differences between means. Remember that that's really a semantic thing about how the data is taken. It's still the same distribution. What we're going to do now, and this is the example from today, that will probably take a day and a half to work, is looking at ANOVA. So if I have three groups, so what happened in this fake study is they gave people snacks and then asked them to rate how healthy the snacks were. So clearly cheese is going to be the best favorite snack because I love cheese. So they have cheese, we have candy, and we have fruit. And so we have three groups. Everything we've done so far has been either one sample or two samples. Now what happens when I have three or more? 4, 5, 6. So what could we do? Well, we could do what are called pairwise t-tests. So independent t is essentially a pairwise t. What does pairwise mean? That means 2 at a time. So anytime I see pairwise, I think like the Noah's Ark of t, 2 by 2. Okay. So 2 at a time. So I could do group 1 versus group 2, 1 to 3, and 2 to 3. So cheese to candy, cheese to fruit, candy to fruit. So I had every mean compared to every other mean. And we actually will end up doing that at the end, but it's a little too easy. That would make life a little too simple. But the theoretical reason on why not, so why not use multiple t-tests, is that most people consider that cheating, but the cheating this time has a name. It's called fishing. Because you're fishing for a finding. You're just trying to find something. And so it's a type 1 error issue. Remember that type 1 error is rejecting the null when you shouldn't. So we said something is significant and we shouldn't have. And we've defined that as alpha. So alpha, remember, is our critical p. So they all have the same name. And that's what we set p as at the beginning of our study. So when you say p less than 0.05, what you're really saying is that alpha is 0.05. So we're okay with rejecting the null when we shouldn't 5% of the time. However, when you run multiple tests, the error rate goes up. So normally when we do independent t, it's just one test. So our formula here, 1 minus alpha to the c. If I have one comparison, this becomes 1 minus alpha to the 1. And if alpha is 0.05, it gives 1 minus 0.95, which becomes 0.05. So if I only do one t-test, it reduces back to alpha. If I run more than one t-test, it doesn't, though. And because we all know how good at math I am, there's a chart in here. So if I have two means, that's one t-test, and then the probability of a type 1 error is 0.05. That's what's on the board. If I have three means, 1 minus 0.95 to the third. Forget what that is. I know the final answer. I have this chart memorized, mostly because I can't ever do the math. Right? So 0.95 to third. not 0 to the third, I know that. Yeah, 0.8786. So the type 1 error rate increases to 14%. And then you don't have to memorize this formula or this chart, but this chart just makes it easier so you don't have to remember the math. So what happens is, as we run more tests, as we add means, the number of possible tests increases. It's not quite exponentially, but it's close. So with 3 means, I get 3 tests: 1 to 2, 2 to 3, 1 to 3. If I have 4 means, 1 to 2, 3, 4, 2 to 3, 4, 3 to 4. So I got 6, 5. It's 10 tests. And so the number of comparisons line, where that number is coming from, is the number of possible 2 by 2s, or 1 by 1s, if you will. So if you have 7 means, it is 21 possible comparisons. So at 4 groups, or 4 means, you have over a 1/4 chance of finding something that you shouldn't. If you have 6 means, half. Okay. And so this is a problem that's out here. So we have to do something to fix that, and that's what this chapter is about. So one of the things we'll do is use F instead of T. I'll tell you in a minute about how they're all related. And we're going to use ANOVA. ANOVA is a very cute acronym for analysis of variance. That's cute. Yeah, I know. It's kind of funny because in R the abbreviation is AOV, which makes a little more sense, but ANOVA is easier to say. Okay, so analysis of variance. ANOVA is used when you have 1 or more nominal independent variables. So I can use multiple IVs. We're not going to cover that in this class, but you actually could use separate independent variables. So this really should say 2 or more levels of an independent variable. And at least they scale dV. So we're still working with the dV has to be scale and the IV has to be categorical, but we moved from having 2 levels, right, 2 samples, to 3 or more samples. The nice thing about ANOVA is it's not like, with independent T, it's like, this slide. With independent T, it's 2 samples only. With ANOVA, it's 3, 4, 5. It's as big as you want. I mean, you don't want to do 27 samples, you'll go nuts. But it's not like there's 1 test for 3, 1 test for 4, 1 test for 5. This is like 3 and up is ANOVA. So we're going to do a one-way test. And the nomenclature on ANOVAs is a little ridiculous. That's the only marker we have. Anytime you see a number, so like this, and then the word way, all this means is IVs. And this is the number of IVs. So a one-way ANOVA has 1 IV with 3 or more levels. A 2-way ANOVA has 2 IVs with 3 or more levels, right? 2 or 3 levels. So all this does is tell you the number of IVs. So an example of a one-way test are cheese, fruit, and candy example. So the IV is type of snack, and these are the levels. I talked about levels as a term a while ago. That really means groups. What are my groups? An example of a 2-way design, kind of have to draw it as a square. Cheese, candy, fruit. So here's 1 IV, snack. And maybe you wanted to look at that by gender. So we would have 2 separate variables. We were interested in the combination of them. So in this design, we're just asking, in the one-way design, we're asking, are there differences in snack preference? But if you made it a 2-way design with gender, it would be differences in snack preference by gender. we're only going to do the one-way designs, but it helps if you see kind of both of them together to understand what I mean by number of IVs versus number of levels. So when they're asking about the number of levels, it's the number of groups in the study. And then actually it's more tricky down here, but if you just keep levels as groups, you'll be all right. So for it to be an ANOVA, you have to have at least one IV and 3 levels. For a two-way ANOVA, there's 2 IVs and at least 2 or more levels for each one. And so that's why this slide says, if I back up, we're in 2 or more nominal variables. They're talking about you couldn't use 1, but they got to have at least 2 levels. We talked about within groups and between groups before, and this is going to get, like, the terms are so horrible, it's terrible, and I'm sorry in advance. So we did, let me draw you a chart. I like charts. So we talked about between subjects designs. Okay. Each person's in their own group. And then we talked about repeated measures designs. So this is the type of research method. So it's the way you collected the data. For these, the type of t-test was an independent t and a dependent or paired t. So the t-test depended on the type of research design. Same with ANOVA. They've got matching set of ANOVAs. A within groups design is more than 2 samples with the same participants. It's called repeated measures. More people call it repeated measures now, because then they at least match. And then a between groups design, where there's more than 2 samples or between subjects, where everybody's in a different group. So if I do this type of design and I have 2 levels, it's an independent t. If I have 3 or more levels, it's an ANOVA, between subjects ANOVA. If I do a repeated measures design, everybody takes every part of the study. If there's 2 levels, it's dependent t. If there's 3 or more, it's within or repeated measures ANOVA. We're only going to do this one here, because we just don't have time to do all of them. There's like 12 different types of ANOVA. It's annoying. We're going to do one. But this is all about the research design, telling me what type of test to do. It has nothing to do with the math of the test. Unfortunately, the names overlap. So make sure you get that this is about whether or not they take only 1 level or they take all the levels. That's the big distinction. So if you were in the study, you would only do 1 level or be in 1 group. If you were in this study, you would be in all the levels. So class is a repeated measures design. You take every test and quiz. If I was comparing your class to my friend's class, that would be between subjects. You could only be in one of them. And the cool thing about ANOVAs is you can mix and match as well. So if I have 1 between subjects and 1 repeated measures, it's got a mixed design because I've got 1 of each. So is this where I talk about how they're the same? Yes, okay, good. But since we have 3 or more levels or groups, I can't use t anymore because the whole point of t is that there's only 2. It's mean minus mean in some form. Mean differences or differences between means. So I have to figure out a new solution because I can't just do mean minus mean minus mean because I don't know what that implies. So instead we're going to use the F distribution. F is the friend of t, who is z. Okay, So they're all emulating Z. They want to be Z in a perfect world. I guess Z is our model distribution, if you will. But we love distributions of all shapes and sizes. Sorry, I did so much eating disorder stuff this weekend. That's all I can think of. I'm like, Z is the perfect distribution. But we love all distributions. Y'all are laughing. It's Monday. Come on. No. It's like thesis week. So all I've done is read theses this week. So Z is our normal bell-shaped curve distribution. When we talked about T, it depended on the number of people that you had. So that's why we had that whole degrees of freedom thing. But T becomes Z when N is around 100. So when you have at least about 100 people, T and Z are the same. And so the real difference between T and Z is that estimation of standard deviation. And then when we get to F, F has 2 degrees of freedom because you've got more than 2 groups. But the nice thing is if you take T, square it, you'll get F. So the F distribution is T folded in half. It is T squared. So they're all related to each other. Z's are our like perfect distribution. So if T has enough people, it is Z. And if F has enough people, right, it's T squared, which is Z. Why is it squared? Well, you see in the formulas we're going to work with variance. So the whole thing, we never take the square root, ever. It's all variance, all the time. It actually makes life a little easier because you can only do a one-tailed test. There's no other tail to have. And so essentially we always do a difference test. So it's weird. There's only one tail, but you're always going to do a two-tailed test. I know. Because you've taken both tails and folded them over here. So you pretty much always have to work with 2 of them. We'll get into that more in a little bit. You can't have a negative number. If you get a negative number, you have made some magic math happen. Okay? It's always squared. Now, this 2 degrees of freedom thing has to do with the number of groups and then the number of people. So the first degrees of freedom is about the number of groups, and we'll do this after the formulas and stuff here in a little bit. And then the second degree of freedom is about the number of people. Here, the only thing that mattered was the number of people, because the number of groups is always the same. Because F has a variable number of groups, we have to include that in our understanding of the distribution. So this is just different examples. So df1 being 1 and df2 being 1 is this black line, which essentially means you have 2 groups and 2 people in each group, which is not a very good study. You have 3 groups, they get shorter. But the more realistic numbers to look at are the green one, this green one here. Okay, now that's got 2 people in it. Maybe this gray one, yeah. So if I had 101 groups and a whole lot of people, right, it would peak here. So the thing to notice is that where most of the distribution is, you don't have to memorize this, just an example of how it changes. You'll see that most of it is 1 or less. And we'll get into why are they always so, the numbers low in a second. So this is a slide that just explains like when you would use each distribution, and then it explains what I had over here. So the Z distribution is the best distribution in a sense. T is the same as Z if you have a very large sample, which is about 100. It says infinity, but 100 is close enough to infinity in math terms. And then F is Z squared if you have a lot of people, or T squared if you don't have a lot of people. So while this is going to seem like it's pretty different, they're all based on the same principle of mean differences are 0. And then we are dealing with variance this time, so it's all squared. Because remember, the name of it is analysis of variance. So no standard deviations. So this is a slide we used last time. So we've been doing mean minus mean over standard error. Mean minus mean, standard error, mean minus mean, standard error. Even the crazy standard error for independent T. Still standard error. What do I do now? Because mean minus mean minus mean doesn't make a lot of sense. if I just had two groups, let me go back to my picture here. If I just had these two groups, mean minus mean would tell me how different they were. But if I took it's 6, 2, and 5, and I subtracted those, 6 minus 2 is 4, minus 5 is -1. I don't know what -1 implies. Okay. Is one of them difference is large and the other one's not, which is what's happening here, right? These two are very different than this one, but these two may not be different. Or are all the differences small? Like, I don't know. So we have to come up with a new set of rules, basically, to deal with the fact that we've got 3 scores. So that's the big issue. So we're going to use the F distribution. The F distribution is still an odds ratio. So mean minus mean over standard error is the odds of the mean difference being larger than the error. What we're going to do now is the odds of the differences across all of them being greater than the error. So it's still based on the same idea of differences between scores over error. But we have multiple scores, so we've got to deal with the fact we got 3 or more. So it's the variance between groups over the variance within groups. Or the way I like to think about this is the model variance, because then the terms don't overlap research methods. The model, my IV, the thing I want, or you can call it good variance in your head, over bad variance, error. So it reduces down to the differences in the sample means divided by the average of the sample variances. We're going to do this like I say by hand, but I don't really mean by hand, like sort of by hand, so that you can see where these numbers come from. So why are we using this weird statistic? Other than I told you you're supposed to. And then what I'm kind of doing, I think, is this slide. No, this one. So if you want to write on this one, this is where I'm going to draw it and explain what's going on. So let's say we have our 3 groups, our cheese. So the health rating was 1 to 10. We had a group at 6, a group at 5, and a group at 2. So here's candy. They don't think it's very healthy. Probably a good thing. Fruit, yeah, but I don't like it that much. The cheese. So we've got our 3 groups. And we're looking at the ratio between groups first. This is between groups variance, which is not like moderately unrelated to between subjects design or between groups ANOVA. I know, it's terrible. That's why most people call it model variance now. Because, like, I think they just got bored making up terms and used the same ones over and over again. So between subject design or between groups ANOVA is about the fact that everybody's in a different group. Between groups variance, slightly unrelated. So what am I doing? So between groups variance is this idea that I have these means. So my 2, 5, and 6, and I want to know how different they are. I already told you can't just subtract, because 6 minus 5 minus 2 is -1, and it doesn't make sense to just subtract them. So instead what we do is we create a grand mean. It's the average of the average. It's not that exciting, really. The grand mean. It's got a crown. And we subtract everybody from the grand mean.
Oh, so is it like creating a kind of effect size? Or is that big complicated?
Effect size is slightly different. We'll get to that in 30 slides. In some slides. I know, like yesterday I was making these, I was like, they're going to freak out when they open the number of slides this is. Because I know we've been doing like, oh, there's only 20 slides, it'll be fine. This one's like 60, I think.
59.
Yeah, I was close. I made them on the bus yesterday. They'll be fine. It's because there were lots of examples. Alright, so between groups variance or model variance is how different are the groups. So we're looking at the variability from the grand mean. So when I have multiple groups, what you do is you basically find the center and you figure out how far away everyone is from the center. We're going to divide that by they're going to call it within groups variability. And I get why they call it between groups variance, because it literally is the means of each group subtracted from each other, or from the grand mean. But I wish it didn't overlap with between groups designs. Within groups variance is how much people vary from their own mean. So it's the standard deviation of the variance for each group averaged. So what we're doing is taking how far apart they are from each other and dividing how much variance they have within each group. So you want skinny distributions because you have less error variance. And to me, the logic of this is like, if I did my study correctly, the differences between group means, okay, the between subjects groups should be large because I did something to them that pushes the means further apart from each other. But within groups, I don't know why that people vary. So I don't know why everyone doesn't rate cheese as a 10 because they're crazy. Right? So the rating for the spread around the mean for the cheese group is just individual differences is what you'll hear it called sometimes. So some people like it more than others, but overall I think it's probably more healthy. Right? Some people might really like candy, so their group, the spread around each group is error. I don't know why people picked something other than the mean. And that is the same type of error that we used when we did independent T. Right? We took both groups and we figured out a weighted average for variance. I remember we had like degrees of freedom times variance. Same thing here. It's a weighted average. And this is the more technical definition. So between groups variance is the estimation of population variance based on differences among group means. So the important part here is to get that it's this last part. It's about the means. How far apart are the groups from each other? Within groups variance is the individual variances for each group. Okay. So I include the book terms here because there's I think a question or two where it gets you to distinguish between the two. So between groups variance is about the differences in group means. Within groups variance is about within each group what are what's their spread. So I like to think about this as good variance to bad variance. Group differences are what I want to have happen in the study over I don't know why their individual groups are different. Yeah.
Is it kind of like if, it's a horrible analogy, but it's like, is the between groups kind of like if you viewed like your distribution as a neighborhood, it's like you're checking to see what the neighborhood is like, but if you look at within groups, it's like within each house. It's like within each one of the little,
Yeah.
I'm
I might
sorry,
do cities.
Yeah.
How different are the cities, and then within groups is more like why are each of these little neighborhoods different?
Okay.
Maybe.
Yeah. That makes sense.
Not a bad example. It's
I
just,
think in analogies, I'm sorry.
no, it's fine. The way I think about, you could take a better example, and no offenses to anyone in Greek life would be the difference like fraternities and sororities.
Mm-hmm.
So across groups, they present these these pictures of this is what our sorority or fraternity does, but within the group, there are people that feel differently about those things.
Okay, that makes sense.
So across groups to me is like, what is the big picture for this group, whatever it is? You know, these are just silly ratings of healthiness. But within group, why do they vary around that idea?
And when you get down to it, the big reason that like between each one of the groups is the actual test you're doing, and within would be like the confounding variables, right?
Individual differences is a good way to think about it. So
yeah.
People vary just a little bit. Because people are weird, they vary a little bit.
We don't like people who like statistics.
All right, so this slide is what I have drawn on the board. But if I look at A here, and I'm thinking about, this would be a great slide to stop on because the next one's all about the math. If I'm looking at the spread of the distributions around A, so it's got its little dotted lines for the means, right? They all appear to have about the same variance. So in these first two, the variances are roughly equal. So the difference between A and B is the spread of the distributions. So for A, you're going to get a small F ratio. Right? because the means are not very different between groups. Then within groups, they have a pretty big spread. So that ratio is going to be fairly even. So if we had A here, okay, our means are kind of close together. So the top is going to be a small number, and the bottom is going to be kind of a large number for the F ratio. My means are not very far apart, and the spread is kind of wide. So this is going to be a small f. That's bad. We want a large F ratio. We want the good variance to the bad variance ratio to be big. So remember, these are odds ratios. So the odds of your study working over not should be a large number, just like we want T to be big. Now in B, what we've done is spread the means out. So what we've got is kind of a larger ratio to, I still got the same error. So that's going to be approximately 1. It might be a little bigger than 1, but the ratio, the spread is large between groups, but also within groups. And that's also not good for you. Now C keeps those same mean differences, but squishes up the bottom. So we're talking. The top is large and the bottom is small. And that's when F will be big. Yay, and that's what you want. So in perfect world, we've got C, where there are clear mean differences and the populations don't, or the distributions don't overlap very much. And so the spread of the distributions is kind of small, so that the denominator is small, and the differences between means, so the group picture, is a large difference. So there's always a question in something somewhere about what an F ratio should be. So kind of coming back to this slide. So F ratios of 1 or less are really common because the variance, the ratio of the variances is the same. It's basically a hot mess, is the way I describe it. Okay. It's a non-technical term. Because you might have large group differences, but it's overshadowed by large errors. Or you might have small group differences with really large errors. So anything where you have a large denominator, okay, large is a relative term here, but just think bigger error, F is going to be about 1 or less. Because the odds of your experiment are 1 to 1. We don't know. It might be because of your experiment, or it might just be because people are weird. Does that make sense, people? So 1 to 1 ratio is not good for you. It might be in gambling, but not in statistics. What I want is a really large ratio. So anything bigger than 1. And really 5, I think, is what they kind of talk about in the book. Anything a 5 to 1 ratio will pretty much usually be significant. But anything larger than 1 is more than likely to be, is going to be significant. Anything 1 or less is not, ever. Yeah.
Is this like, okay, so I know we a lot of times we use like alpha critical, so like 0.05 is like what you have to find. So like when we're talking about like the actual alpha though of the statistic, would
You're talking about P found?
Yeah, like
P in our study?
Yeah, P found, and the small over large and the large over large. P found is going to be pretty large because the error is large, right?
Yes.
So the first two.
P values in these two of the actual study are going to be large, which is bad.
Yeah.
Right. Because F is small. They work in the opposite direction.
Yeah, because there's a really high chance of having an error, which is a type 1 error.
Right.
Yeah.
In this sort of study, that's where P gets smaller because the likelihood of finding larger or small is smaller.
Okay. Oh, that makes more sense.
Yeah. The P for your study, which it gives you in the output, and the statistic are going opposite directions. The larger the statistic, the less likely you are to find such a big difference, so you get smaller P's. Because remember, null hypothesis testing is totally backwards. You want small probabilities because it's a probability of making a mistake. Now, alpha or P critical, we almost always set at 0.05 or 0.01. That pretty much stays the same.
Yeah.
P from your study will change based on this ratio.
Yeah, because I feel like that always helps me, because if I can come back to P, it's the amount of, and that's the same through all the studies.
Right.
Like the alpha, yeah, that
Yep.
really helps.
Okay, so